Okay, in this video we're going to look at the work done by a polytropic process. So basically what happens is that in thermodynamics, every time there is not every time, but in many cases, every time there is an expansion or compression of a liquid or a gas, generally will follow a polytropic process. In most cases it will be for a gas, but it also works for fluids. So basically, what's a polytropic process? So you have a line. I'll plot it this way. As long as you don't make a straight line, it doesn't matter. It will be correct. And this will be V1 and V2. And actually, this is the PV diagram. And graphically, the work done is the integral under the curve. Okay? But let's just see what happens over here. So what is the definition of a polytropic process? So a polytropic process defined as the product of the pressure times the volume times a constant n. Sometimes they call it K or gamma, but in most textbooks they use the letter n, should be equal to a constant. Okay, where n here is the compression expansion gas constant. So expansion, compression, constant. Okay, so now we need to differentiate two cases. So case 1 would be, let's say, for n equal 1. So in that case, what do we have? We have PV n to the 1 equal to a constant C. Okay? And we need to find what is the work done by the pressure. So like before, we find work done by the pressure equal to plus or minus, depending on the definition given for the first law of thermodynamics, P dV. So from the above equation over here, we can rewrite that P will actually be equal to what? C divided by the volume. So if you come over here, this will be equal to plus minus integral of P, which is C over V dV. Or we can just rewrite this as work of pressure equal plus minus C, I put the constant outside integration sign, integral of dV over V, and we will integrate between, let's say, volume V1, V2. So this will give us that the integral, that the work done by the pressure is equal to plus minus C, and the derivative of this will be log of V between V1 and V2. Okay, so here now I'm going to start simplifying the expression. What is C? C is a constant equal to P times V. So you can either choose here, C could either be equal to what? P1 V1, or it could also be equal to P2 V2. this case, I think we're just going to use this one. So what does that mean? That the work done by the pressure equal to plus minus P1 V1 times log V2 minus log V1, or we can just rewrite this as plus minus P1 V1. And you might remember, I'm going to put on this side, put that log of A over B equal log of A minus log of B. Okay, so using this relation, and then you have that the work done equal to log of V2 over V1. Okay, so I'm now not going to write it, but I'm just going to mention over here that sometimes you can write the same equation using the ideal gas relation. PV equal N RT, so you will see this will be equal to what? N RT1, and you can write, you can leave this as V2 V1, or you write it in function of the temperature and the pressure. Okay, so that was the first case when N equal to 1, but we can have the other case when N is different than 1, okay, and different than 0. So for case 2, okay, I'm going to keep the notation simple. Basically, let's just say N different than 1, and should also be different than 0 and positive. But I'm going to keep the notation simple, okay? So again, we have PV this time, PV to the N will be equal to the constant. So we follow the same process as before. From here, we could say that the pressure is equal to C over the N. So that now when we go and calculate the expression for the work done by the pressure, equal plus minus P dV, so this would be equal to what? Plus minus P is equal to C over Vn dV. Okay, so we can just rewrite this as work done by the pressure equal to plus minus C, I put it outside the integral sign, of dV over Vn. Okay, so over here, I know you know how to do this integral, but just because the way it's written, sometimes you get lost. So what is the integral of, let's say, x n dx? You all know that this will be equal to x n plus 1 divided by n plus 1. So if you follow the same reasoning, what would be the integral of x to the minus n dx will be equal to x to the minus n plus 1 divided to the minus n plus 1, which is the same to 1 minus n. Okay, so if you look at this equation actually is the same as writing this as plus minus integral of v to the minus n dv. So if we do this integral will be equal to what? Plus minus c. Okay, and now the integral of v minus n dv will be equal to what? V of minus n plus 1 divided by 1 minus n between V1, V2. So now this will be equal to what? Plus minus C V2 I can put the 1 minus n over here, so V2 to minus n plus 1 minus V1 of minus n plus 1. Okay, so now the trick for this one is actually to move this C into each one of these terms. So basically this is the C, you put it over here. V2 minus n plus 1 minus C V1 minus n plus 1. Okay, and what is C? Remember from the above equation here, C, so C will be equal to P V to the n. So that means that C can either be equal to P1 V1 to the n, or C could also be equal to P2 V2 to the n. So for this C over here, we're going to use this expression, and for this C over here, we're going to use the first expression and see what happens. So over here, we're going to have work done by the pressure equal plus minus 1 minus n times P2 V2 to the n times V2 to the minus n plus 1 minus P1 V1 to the n V1 to the minus n plus 1. And you can probably see right away that this V2 to the n will cancel out with this V2 to the minus n. This V1 to the n will cancel with this V1 to the minus n. And at the end we have that the work done by the pressure equal to plus minus 1 over 1 minus n P2 V2 minus P1 V1. And as in the previous case, I mentioned that sometimes if you use the ideal gas relation, PV equal nRT, this will become what? 1 divided by 1 minus n R T2 minus R T1. Okay, so now let me just do a summary of the previous video of the work done by constant pressure, and this is the work done by a polytropic process. So basically we have that so let's do a summary of all cases. So for constant pressure, we had that the work done by the pressure equal to plus minus P V2 minus V1. Then for a polytropic process, which means PV to the n equal to a constant. Okay, let me add here a couple of figures, so if you want to do it graphically. For this case over here, we did show that if the pressure is constant between 1 and 2 and V1 and V2, the expression of the work is given by plus minus P V2 over V1, where the work, you could also find it graphically. For a polytropic process, you had a similar figure. So the area again is the work, is the area under the curve. Okay, so in here we had two cases for n equal 1. We found that the work done by the pressure will be equal to plus minus P1 V1 log V2 over V1. And for n different than 1 and 0 and being a positive integer, the work done by the pressure is given by plus minus 1 minus n P2 V2 minus P1 V1. Okay, so that's basically the summary of equations that we have. Okay, so maybe let's look at the system. So let's do a general summary of this, of everything so far. Probably I'll do it on a different video to summarize everything. So that will be the end for this video.